Hello, in this video I will present an easier and intuitive derivation of second order and fourth order Runge Kutta methods. There are several ways to derive the relations for Runge Kutta methods. The one that I will present here is easier to understand and much more intuitive. The basic problem of finding a numerical solution of a first order differential equation like this is to have a relationship like this, that we can predict the next value of this function y based on the previous value in a relationship like this. So let me call whatever the function here is approximately slope. So the idea of better and better method is to find a better and better approximation for this slope. If I show it graphically, suppose we have a function like this. So we are given the slope of the function, and if we start from, let's say, this point xn and want to find this point xn plus 1, we can have let's say a straight line interpolation from here to here, and then this interval is h, and whatever the slope of that line is, we put it here. Okay, so for example, Euler's method is the easiest one, where slope is just the value of this function at this point. In backward Euler method, the slope is just the value of this function at this point, and so on. So let us now discuss a general framework with which we can derive this simpler Euler or backward Euler methods, and few others, including the Runge Kutta methods. Okay, so let's begin from this differential equation, which is an initial value problem. That is, that we are specified that at some initial point x naught, we are given the value of the function, and we are supposed to find the value of y between an interval, say from x naught to some capital N. So we have to find the value of y in this interval. This is our problem. Okay, so let's begin by converting this interval x naught to some xn into discrete points, let's say x1, x2, some xn, some n xn plus 1 up to xn. So if we have divided our interval of interest into this partition of x, our goal is to find y0, y1, y2, y3, and so on up to yn at each of these points. To do this, let's begin from this equation, and let me note that this y on the right side is also a function of x, so this is actually f of x, y of x. So let's integrate both sides of this differential equation from an arbitrary point xn to the next point xn plus 1, like this. Now on the left side, we can quickly get this, and we get different methods by having different approximation to the right side for let's say using Taylor series. So let me write it like this. This is xn to xn plus 1 f of x y of x dx. So if I use, let's say, only the first term in a Taylor series of this function that I write at x naught or some point xn, then we can quickly get Euler method. So let's do it. So Euler method. We quickly get it if I can take this yn to the other side. If I approximate this using f of xn, some y of xn dx, because in this case this is yn and this is just a constant number, and let us define this h as xn plus 1 minus xn, which is the width of the interval. So we have h f of xn, and this y of xn, let me use symbol yn. So this, as you see quickly, is nothing but Euler's method. However, if instead of approximating this function at xn, if we approximate it at the other end of this interval, that we approximate this f of xn not here but here, then we get what we call backward Euler's method. And let's see how. So I can write this yn plus 1 as yn. This goes to the other side. And let's now approximate this as f of xn plus 1 y of n plus 1 dx. So this is approximation, and we can now solve this integral quickly right away because this is a constant function yn plus h f of xn plus 1 y of n plus 1. So this is the backward Euler method. Of course, in this method, we first need either, if you want to use equation as it is, then we might have to use some root finding method to find yn plus 1. But sometime we can use a simpler method to find this guess value. For example, we can find this yn plus 1 using this forward Euler method and just plug this yn plus 1 here and then compute the sort of correct yn plus 1 using this method. So we see that these two methods are essentially the same. There's only a difference of approximating this f at two different values. So that's why they both have the same order of error, because if we think of the Taylor series, we are neglecting the terms of the order of h from this expansion. Okay, so for the next order methods, for second order methods, so Euler's methods are first order method. We need better approximations for f of xy. There are several ways to get second order methods, but let me get it using this approximation, that I can approximate this f of xy with two terms in the Taylor series. Or let's say this is xn plus half yn plus half. So here I am approximating this function actually as the central point between xn and xn plus 1. So this xn plus half is essentially xn plus half h, or you can say this is nothing but xn plus 1 by 2, and this yn plus half is yn plus half h. Now we need slope of the function here, and there are several ways of finding this slope. For example, forward Euler method or other using other methods, and from there this I can compute this, or we can also approximate it like this. Okay, so if I use this approximation and I'm neglecting the remaining terms in the Taylor series, because the next term would be, let's say, x minus xn plus half f derivative of xn plus half yn plus half. The next term is x minus x n plus half square by 2 f double derivative. Then still the next term is q triple derivative plus x minus xn plus half power 4, 24, fourth derivative, and so on. So this is actually just the Taylor series of this function around point xn plus half. And if I keep only this first term, or actually we can keep two terms. Let's keep these two terms. So then I get yn plus 1, yn plus xn plus 1, and now I have the approximation for this function as this, plus x minus x half f prime of xn plus half yn plus half, and I'm neglecting terms of the order of h square from this. Okay, so now we can do this integral quickly. This is yn plus, so this is constant, I get h f of xn plus half y of n plus half, and its derivative would be plus x minus xn plus half squared with n plus half here over 2 f prime, and integration limits are xn to xn plus 1 and plus. So this term in the integral was, so this dx should have been here. So this term is of order of h square, so the integral would be of order h cube, and it has also be to be integrated from xn to xn plus 1. Okay, now we have this simple relation. So this remains as it is. We can see quickly that when we put xn plus 1 here, we will get h by 2, because the difference between xn plus 1 and xn plus half is h by 2, and there's a square. Then we will have minus, and then we will put xn here, and we will get minus h by 2, but its square will be plus h square by 4, and when we subtract this from the other term we get 0, so its effect goes away, and over here we have the sorry, this is not there because when we talk integration, h cube is already there, and we now have terms of the order h cube into second, into third, into second derivative. Okay. Now, from now on, I'm going to neglect this, but you can see that the order of the error in this term is of h square in terms of xn and xn plus 1. The reason is this, that I can expand this double derivative in terms of the first derivative, and that will have an h under this, and this is xn plus 1, this is xn plus half, so derivative will involve xn plus 1 and xn. And this 1h will be cancelled, so the order of error in this method is h square. So that's why it's called a second order method. And the terms that we now have are this. So second order method is like this: yn plus 1 is yn plus h f of xn plus half yn plus half. This, by the way, is also called midpoint method, because this is essentially the midpoint of xn and xn plus half. So this is a Runge Kutta method of second order, or you can also say this is a midpoint method. Now, this method can be implemented in several ways, because we have yn and we have xn. We can compute xn plus half very easily, but to compute xn plus half, yn plus half, we need some other method to predict this value. So the easier could be that we can use Euler method, forward Euler method, to find this in terms of y and xn, and then once we have the value of this function, we can use it here to find yn plus 1 from here. So let me call this k1, which is the slope in the Euler method. So this is xn, yn. So if I have this k1, my yn plus half would be yn plus h by 2 k1. And let me call, so once I have this yn plus half, I can define a k2, which is nothing but f of xn plus h by 2. So this xn plus half is xn h plus h by 2, and this yn plus half is this, which is yn plus h by 2 k1. So once I have this k2, yn plus 1 is equal to yn plus h k2. Okay, so this is one implementation of second order Runge Kutta method. Let me call it RK2. So here, to compute yn plus 1, you need yn and you need k2. And to find k2, you need k1, and k1 is here from forward Euler method. So using k1, k2, I can find yn plus 1 at every step. This is Runge Kutta method of order 2, and this is also called a midpoint rule because of its form, where it is midpoint. It's like midpoint. And from here we see that this is a second order method, because when we were integrating this Taylor series of the function around this xn plus half, yn plus half point, this term cancelled away and our order of error is proportional to h square. Okay, so now actually there's another alternative implementation of RK2, and let me see that. Let me just write it. So this alternative implementation of RK2, we call it alternative. RK2, that what we do, that we approximate this xn plus half yn plus half function by xn yn plus xn plus 1 yn plus 1 over 2, which means that our yn plus 1 is yn plus h by 2 k1 k2, where our k1 is f of xn yn, and our k2 is f of xn plus 1 yn plus h k1. Because for k2, which is actually this term, I am approximating this yn plus 1 from using the forward Euler method by yn plus hk1. So with this k1 and k2, we have an alternative implementation of Runge Kutta second order method, which is here. And this, by the way, is also called trapezoidal method. So this implementation of RK2 is also known as trapezoidal, because if we approximate the function, if we see the function like this, and then this is point xn, this is point xn plus 1, if we approximate this curve between these 2 points by a straight line, this is almost a trapezoid. And if we use this representation for f of xy to approximate with a line, and we integrate, we get the same result. Okay, so this is how we derive RK2 method. Let's now see how we can get an even better method, which is fourth order, because the error in that method is proportional to h power 4. So let's now derive the fourth order method. Now let me use this graph here. So in the fourth order method, what we do, that instead of approximating the curve with a straight line, we can approximate it using a second order polynomial, and for that we will need a central point xn plus half. And just to recreate, this is length h, so this length would be h by 2. So we use a second order approximation of the curve between in this interval, and using this second order approximation we can get a higher order method from this RK2. Okay, so let me get back here. So just to start from the beginning, we have this equation, and we integrate it from xn to xn plus 1. Now the left side is easy. On the right side, I use full approximation for this function, which is a Taylor series xn plus half yn plus half. The next term is x minus xn plus half. First derivative evaluated at xn plus half yn plus half. The next term is x minus n plus half square over 2, no double derivative, evaluated at the same point, plus x minus xn plus half cube, 6, f triple derivative, then x minus x n plus half power 4, 24, and fourth derivative, and so on. Okay, so this gives us yn plus 1. We take it to the other side, yn. This is a constant function, so integration over length h is just h times f of xn plus half y of n plus half. And now the integration of this function would be 0, as just we saw for developing second order method, because when I will integrate this, I will get a square, and once I have a square and this point is in the middle of my integration interval, I will get 0. So this term will only give me 0. From this term, I will get x minus x n plus half cube over 6 f double prime. Now similarly, this is a cubic term, so its integral would be fourth power, and when I will put two values for x, I will get 0, so this is 0, and from this term I will get a term which is of the order of h power 5 into fourth derivative. Alright, so we have yn plus hf xn plus half yn plus half plus. Now, just as we did when we were developing Simpson's 1/3 rule, let's first put, there's a limit xn to xn plus 1. So when we put xn plus 1 here, we will get h by 2 power 3. When we put xn here, we will get minus h by 3, h by 2 power 3. And since there's a minus sign when we are putting this, we will have total plus. So we have 2 times h by 2 cube over 6. Now this is a double derivative evaluated at this central point, which I can write it like this right now, and then so this is a double derivative at xn plus half yn plus half, and then there is a term which is h power 5 and fourth order derivative. Okay. Let me go to the new board. So let's continue. Yn plus 1 was yn plus 8 f of xn plus half, yn plus half plus 1 over 3 h by 2 cube. And for f double derivative at xn plus half yn plus half, we can expand as f of xn yn plus f of xn plus 1 yn plus 1 minus 2 f of xn plus half yn plus half over h by 2 square, which will give us yn plus 1 yn half plus, now this h by 2 cube cancels with that and we are left with h by 6, and inside we have f of xn yn n plus 1 yn plus 1 minus 2 f of n plus half yn plus half. And we can combine all of this yn. Let me take h by 6 common. So I have 6f here and there is this minus 2f same. So we get this as it is, f of xn yn plus 4 f of xn plus half yn plus half plus f of xn plus 1 yn plus 1. Now this is what we call RK4, or Runge Kutta method of order 4. And there are several implementations. There are several, because to find yn plus 1 we actually need yn plus half and yn plus 1 to compute right hand side. So there are several ways that we can do it, and let's say the easiest one is if I define k1 as just this term f of xn yn, and then I can have k2, which is an approximation which is sort of slope for computing yn plus half using forward Euler method. So this would then be f of x n plus half y h by 2 k1. So if I use this k1 as a slope to compute yn plus half, I would actually get yn plus h by 2 k1. So this is nothing but yn plus half computed by Euler method using this as a slope. Okay, and this is now sort of the slope. Let me show graphically here. So this is our xn plus point, this is xn plus 1, this is xn plus half. So k1 is slope here, k2 is slope here, but computed using this point, using Euler method. And k3, let's define k3, is actually a slope which is computed from k2, because so this k2 and k3, they're both slopes at this point, but one is computed using this previous information using forward Euler method, and the other K3 is essentially the slope which is computed using backward Euler method. So you see both of this can be used for this part. This K1 is nothing but this, and this K2 and K3, they can both be used for this slope, but and they can give us alternative implementation. Similarly, for the last term, let me define K4 as f of x n plus 1, which is nothing but xn plus h. And for this I have yn plus hk. So we use K3 because K3 is a better estimate than K2 and more stable as well. So now we have this K1 for this, K4 for the last term, and K2 and K3 for the central term. So there are several implementations that we can think of. Okay, so the one is, so all of these are RK4. I can compute yn plus 1 as yn plus h by 6, this is h by 6, into k1 plus 4k2 plus k4, or we can use this h by 6 k1 plus 4 k3, or better yet, we can use it as k1 plus 2k2 plus 2k3 plus k4. So essentially I'm using an average of k2 and k3 for this middle term. So using this last one is the most popular implementation of RK4 for solving the first order differential equation. Okay, so let me just summarize that using various approximation for Taylor series for this function f of x, y, we can get different methods of different order. For example, we got, if we use the approximation of this function at this point, we get Euler method. If we use the approximation of this function at the next method, yn plus 1, we get backward Euler method. And if we use two terms in the Taylor series that is around the middle point, we got this RK2 method. So this actually had two implementation. This one is trapezoidal implementation, where we use yn plus h by 2 k1 plus k2, and then we had another implementation that was listed here. But if we keep 4 terms in the expansion of f of x, y, we get the fourth order method over here, and we have several options for predicting the values of yn plus half and yn plus 1. And once we use those predicted values here, we can compute yn plus 1 using RK4 method. One of the three possibilities, three of the possibilities are listed here, with the last one being the most common in use. Thank you.